Yeah, no, I'm professor at EPFL, the technical university here at Lausanne, and I have also a second hat there. I'm vice president responsible for information systems, and EPFL has invested a lot in a kind of big data strategy, both in education and research, and that's why some people believe I have something to do with that. But I think there's many people that are working in this area, and not only in computer science and information technology, but apparently now more and more other fields. And I think, if I understand right, this community is very interested in statistics and data analytics, so I'm even not sure whether I can bring a lot of new dimensions into there, at least not from the mathematical side. So that's why I chose to talk more about another dimension in big data analytics, which is the human factor, which seems to me, despite all the excitement about automated analysis of masses of data, remains an essential component. So just, I guess there will be surely posters out there that mention these things. So there are these famous 4 V's: volume, velocity, variety, and veracity. And the first ones are always a lot into in the center of attention, huge volumes and so on, and fast processing. But the second two often get a bit forgotten. Variety, which has to do basically with the many different ways of how we can represent the same information, and this has to do with the interpretation of information through humans, so the semantic dimension. And even by saying it, you mention already humans, right? So you cannot deal with that without involving the human. And for veracity, it is about evaluating the utility, the quality of the information. This is, of course, always with respect to a human dimension, because it's our decisions that we want to make on high-quality data, and the decisions are, at the end, human decisions. So it's quite evident from that somehow humans play a huge role. And I would like just to mention here one point. A lot of this big data is, of course, driven by the big web companies like Google, right? And we have the impression that they completely automate all their processing. But while thinking like that, we forget something very fundamental. They are driven by human input, essentially. They just translate masses of human input into something that's useful for the people in general, or for the business. It depends. That's clear to us that really this capacity to process massive amounts of data, that's something new that we could not do before. And many of the effects that we see have indeed to do with the huge volume. But the more we process this, actually, the more we may observe that human input is becoming actually a very scarce resource, and this is needed to make the processing meaningful. And just to put that in another perspective, so you have heard about the recent successes about using deep learning to solve some of the long-standing difficult problems in machine learning. So, for example, in image classification and similar problems that were thought to be reserved to human intelligence. So machines were thought never to reach the same levels. Now we see suddenly machines even sometimes performing better than humans. And then again, when you think about it, when you see these results, like, for example, automatic generation of caption on images, which, of course, look very impressive. So you give the machine the images, and they write small sentences, right? But then, if you really think about how has this been done, it relies, again, on big data sets of ground truth. So basically, data sets where humans have labeled a lot of those images before, and then you use this information to train the machines. So again, it falls back to what have the humans been contributing to the problem. Now, there are some people that put now the things to the extreme, right? You have surely heard about this, and statisticians will love this, I guess. The end of theory, right? We don't even need any scientific method anymore. I translate this into, we don't need models, we don't need causality. Actually, we don't have to understand anything. Just everything will happen by itself if we throw enough data on the problem. So I think that is probably something where we're a bit away still, right? And I see a lot of nodding heads now, which I'm not so surprised. Now, let's ground ourselves a bit more in reality. So this is another view of things. if you look at a typical task that is performed on analyzing documents, right? So what is a typical task? You would like to recognize entities, right? Who are the people, what are the places that are mentioned, and so on. So that's the problem of named entity recognition, and there exists a lot of technology out there, and it has also, this problem has received a lot of attention in research. Now this is a study that has been done by IBM Research, comparing what has been happening in this field in industry and what has been happening in this field in research. And essentially what you see is, on the left side, NLP papers. NLP, natural language processing, is the key conference in natural language processing. About 75% of the papers were looking at pure machine learning based methods. 25 took the luxury to allow humans to somehow still influence what the machines are doing, and you don't get accepted if you're doing anything where humans interfere with the process, right? This is dirty. Now, if you go to the industrial side of things and you look at the vendors, you see pretty much inverse picture, right? Still, most of the work done on entity recognition, which you can take as one exemplary problem, is based on rules, right? This means nothing else. People are sitting down and thinking hard and writing up a lot of rules and try to solve the problem that way. And the larger the vendors, the more rules are in there, right? So probably this has to do with the fact that some of the research results spill over into startups and give rise to probably some more innovative approaches, but still the reality is that humans play a huge role here. And this is typically the case where you don't have the luxury of Google and others to collect data from billions of people, but you have probably only your 1 or 2 experts in the company that know about the field. And so you cannot train on huge data sets, and you have to ask them probably a bit more precise questions than that. So this is, I think, where we are now. And what I would like to do now is just to give you 3 examples, 3 stories of some things that I've been doing over the past years on how actually this human input comes into the picture when we are solving big data processing tasks. So the first one will be on web credibility, and I've seen right after there will be actually quite a related talk on this similar topic. The second, data integration, and this is something that's kind of very important, because if we talk about big data, we have to integrate first very often a lot of data. And the third, some recent work that we did on social media analytics in the field of food. And I try to give you also some examples that have to do with your focus of your domain of interest to make it probably a bit more entertaining. So this is a typical problem that we encounter today when we go to the web, right? We find a web page talking about some famous diet, and you would like to know, is that something we can believe, or is this complete bogus, what we read, right? So now you won't probably find it quickly, but if you read it carefully, this is a real example. Mr. Atkins died in 2003, and in 2005 he filed for bankruptcy, which seems to me a very problematic statement. So, and so this is probably a good indication that that page is not such a good one at the end of the day. Now, how to solve this problem? Because in general, what's happening today, we have, of course, a lot of incentives to manipulate information for economic reasons, for sure, and others. And we have also a lot of information available, so how can we avail it? So the attackers are trying now to build sites that look very credible. They put a lot of resources in that, and we have to decide now which ones to believe and which ones not to believe. And how can we do that? Now, a first step in that is the following, and that's probably everyone would probably think about it this way. You would say, okay, let's look at these web pages and let's identify features that indicate or don't indicate credibility. And these features can be many. You see a lot of examples. We have identified many more than those that you see here, but you have features that are related more to the social networking aspects. So how is the person connected? How has the page been accessed? And so on. And you have features related to the content. So this can be how many spelling errors are on the page. So it is like in the university, if you get a text and it is full of spelling errors, you will immediately downgrade it because it seems to be not such a good quality. Now, but how can we now learn about how these features relate to credibility? And the obvious answer is we have to first create ground truths. So, and in this field, this has happened. So, for example, Microsoft Research has taken the time to choose carefully about 1,000 documents from the web on several domains like health and related, going to experts, ask them about the credibility, and in that sense, create a corpus where for each page you have a rating, let's say from 1 to 5, and then you have ground truths. Then you apply something that you know extremely well, statistical tests, right? And then you get a ranking or a weighting of which features are very indicative of credibility and which are less indicative. And this gives you some interesting results. So you see that actually, for example, design and readability seem to be very strongly correlated with credibility. Now you may start to develop hypotheses why all these things are the case, right? So we studied, for example, then questions of game theoretic models that explain how much someone is willing to invest into the design to make it credible because of the expected future gain. That's the theory building behind. But you can use that also to simply build then classifiers or models in order to predict now credibility for web pages that you haven't seen so far. So we tested this, and so if you build a classifier, so you just say credible or not credible, you see up there F1 score, so this kind of measures how accurate you are in this classification. You see that, so if you choose just random decisions, you're around 50% correctness, which is what you would expect. If you add content features, you go up to 70%. Social features alone would give you 65%, and both combined get you up to like 75%, right? Or 0.7 F1 score. And this means that in some ways, yeah, you get 3 out of 4 cases or so, you can properly classify your web page, and you can do a regression model where you predict the rating, and you might be off by half a point on average from the correct rating. So it gives you reasonably good models, but of course you still make a lot of mistakes. Now, so this is so what we have nowadays, a state of the art, and it's essentially translating expert input into a model that can predict your credibility. Now, going a bit further, so look at this page here. We didn't test it, but this page would probably get a very high credibility value. It looks clean, it is very nice, and so on. And actually, there is a story behind this page. There is a controversy about autism and the link of autism to external factors, right? And for example, whether nutrition has an influence on autism, right? Now, scientifically speaking, there is no evidence of that, or vaccination is linked to autism. So there are all these discussions around, not with a lot of grounding in reality, but with a lot of social support from celebrities, right? So this is a site that actually is promoting these ideas that autism is linked to nutrition and other things, and you don't see that really on the surface, right? You can start to read the pages, and then you will start to find statements like gluten and dairy seem to affect a lot of our children with autism, and thus we see a lot of children respond terrifically when these are removed from the diet, right? So now, what do we do here, right? I mean, pure surface feature analysis will not kind of reveal such statements that are pretty kind of hidden, well hidden and packaged. And so, that's some of ongoing work we have. We try now to extend this credibility modeling by really digging into the text, extracting such key statements, having a crowdsourcing mechanism where we offer experts to analyze such statements. So there's, of course, a lot of machinery behind, because first you have to find good statements to be evaluated. You have to establish a framework where experts are motivated to participate, and so on. But the idea being that by identifying such statements, and then also have mechanisms to make a semantic transfer, which means if you have one statement evaluated, you can find similar ones, and you may assume they're as incredible as this one. And in that way, you can spread your model to a larger amount of content. And then there is some machine learning going on behind that integrates these various components, starting from the feature analysis over statement analysis, building models of the users, because obviously you can make some inference about users that systematically make incredible, non-credible statements. And in that way, you start to build a model of evaluation that goes much more into the details. So this is the idea, and then to finally get kind of a rating service where you get warnings on sites that are indeed not credible. Now this is just one example of a task that we want to solve where human input is inevitable. It's really at the center of building a method, even if then we build models that are based on machine learning and automated data analysis. And it is very prototypical for many of the things that are going on in machine learning, application of machine learning to different types of problems. And the answer, where is the ground truth, is always extremely simple. You have to ask the experts and the crowd, and everyone who's doing research in that domain knows always this PhD student starting the project and saying, where do I get ground truth data to do my project, right? And fortunately, we have tools like crowdsourcing today, and more generally, this is an instance of what is called in general supervised learning. So you have some ground truth in advance to solve your problem. Now, let me move on to a second example, data integration. So, as I said, data integration is very central to big data analytics because if you want to create big data, very often you have this variety problem. You have many different data sources, and many of you probably know this problem super well. So you have everything from relational databases over text documents, Excel sheets, and whatever else you may imagine. And since 30 years, people in the database community try to solve this problem in a somewhat automated manner, and it is fantastically resisting to every effort to be solved. And the simple problem at the end of the day can be formulated as this example. You have your Excel sheet one name, and you have a relational database with two fields which are called person name and company name, and you don't know what corresponds to what, right? And so this is the problem. Now, the current solutions are doing a lot of thinking and manual work and reading documentation, or there exists some technology that does all kinds of analysis of structural features, of content features of your data. So you could imagine if two data fields have the same type, numeric, they're more likely to match if not, and so on. So this is the kind of reasoning behind. And then these tools integrate such heuristics and make proposals of what would be good correspondences. But you can see, and this is a real tool, but you can see that the proposals are not always unambiguous. So you get multiple proposals, right? So, and still you haven't solved the problem. You have reduced the problem space, but it's not solved yet. And it works only well if you have very small schemas and very few schemas, ideally only two, right? Now, what we were thinking is that in reality, we have, of course, typically more than two schemas, right? A big company today has 10,000s, 100,000s of databases. If you count all the sheets, then it's millions. So you might have many people at the same time trying to solve this problem in parallel. And in this way, slowly, sort of a network of relationships among all these databases starts to emerge, right? And I don't talk about the problem to gather all this information, to make it available or anything, which are completely, but I assume naively now, we would have some way to get all this information, right? What could we do with that? So, come back to our base problem. Now, the nice thing is that if we have all this other data, we establish a context. So it's kind of like a network of knowledge that is around our question. And so what could happen, this is very hypothetical, but you might have now, when you're looking at your two databases you want to integrate, you might suddenly have a third one where the problem has already been solved. And then if you look long enough at this picture, you will just automatically identify which is the good answer here, right? I do not make crowdsourcing now, but I'm convinced that everyone will choose, of course, that C1 is the right answer, right? Because C1 maps to this other field, which maps to this field P name, which maps back to this. It's a perfect cycle, so they must be semantically equivalent. And you can do this kind of reasoning. So this is the answer. you can do this kind of reasoning in a much more general way. You can search for all these types of evidences where you basically observe composed mappings and you see whether they are consistent among each other or not. I will not go into the details of how this will be done. If you're interested, there are very nice papers we have written about it. But the general idea is that you kind of perform a probabilistic reasoning by taking now all these feedbacks. And if you find, for example, a circle that does not close, that's a bad sign. If you suddenly start to map a person name to company name, there's something going wrong here. And this is a bad signal for all the mappings that have been involved. So they get all flagged doubtful mappings, right? And you accumulate all this feedback, do some probabilistic reasoning, and then you get kind of an assessment of which are potentially the better mappings and which are the worst mappings. So this we did. This was kind of a lot of work to do. But it gives you nice results because then you can start to give results that say, okay, imagine all the experts have done this work. Now we can give rankings to mappings and we can potentially choose the better ones and eliminate bad ones, right? So this was the first result. But then we realized one thing, that actually it's probably not the smartest thing to do, to first let all the experts do all the work, and once they have finished, you start to analyze their results, then it's kind of too late, right? So we said it is actually much better if you ask the experts while they're doing work and you provide them immediate feedback on everything you can learn about the impact of their work. So if, so roughly speaking, if we are adding, an expert is now sitting in front of his 2 Excel sheets, he's adding a mapping. While he adds this mapping, this will have a lot of consequences because he might add exactly this mapping that proves that these 3 others are wrong, right? So you should give this feedback immediately, then the expert can start probably either revise the opinion and immediately influences others and so on. So it comes down to the problem of while we are analyzing at the global level all these dependencies on mappings we're generating, we also try to reduce the uncertainty for the expert, for the network by asking the expert continuously questions that are kind of improving the overall state of things. And asking the right questions is there extremely important. So this simple example shows the idea. Say you have the situation at the left and you have 2 possibilities. You have 2 ways to close the circle, so to say. Now you could ask the question to the expert, is the mapping C1 correct or not? So the expert will give you the answer, but you will not learn anything about the rest of the network because C1 is participating to those both circles, so it doesn't add any information about all the other mappings. Would you have asked the question, is C2 correct, right? You would have resolved the problem. So your information gain was much higher. Now from the expert's point of view, it's the same. There are 2 mappings, it decides and so on. From the side of constructing a consistent data integration network, it's very different. You gain much more information with the second question. So this was the underlying hypothesis. And the idea was, can we find mechanisms in order to pose the right questions to the experts to converge as fast as possible to a high-quality integration network. And we did experiments with real data, with synthetic data, and we found that indeed, by having kind of an information theoretic approach where we say, okay, which is the question with the highest information gain, you can save about 50% of the time of the experts, which is, I think, quite significant, right? Normally, if you want to reduce expert time, 10% is a lot, right? 50% is already pretty good. Of course, assuming that we have all this information available and so on and so forth. And even the quality of the resulting mappings tended then to increase as a result of performing in this way. And this is a kind of a second way, so this is different from the way of machine-human interaction we have seen before, where kind of the human does all the work first and then the machine kind of learns from that. Here the machine and the human kind of actively work together to solve a specific task. In that case, data integration, and that's what is nowadays called active learning, which is a second fundamental idea of how to make humans and machines work together efficiently. So let me come to my third example, social media analysis. So we all know, right? Social media, like Twitter, has a lot of hidden signals about what the public thinks about specific problems, right? And so this can be typically on problems that are of a certain general public interest. Nutrition is one that's here very popular, health as well, but can be politics, environmental factors, and so on. And of course, everyone wants to know who are the people that influence those networks, which are the communities, which are the topics of discussion, what is the stance of certain communities, and so on. So, and this is a problem we have studied quite in depth recently, and using basically two types of methods. On the one hand, looking at the content, so what is the text that is produced in these social networks, and on the other hand, looking at the social relationships. So that's very similar to what we did for web credibility analysis, where if you also content-based features and social features. So this is kind of a general underlying theme. Now, the typical process that you perform is the following. So first you come and you say, I'm interested in that. So you give some keywords, you say probably which is the time frame you're interested in, other things. Then you collect the data. And then you start to extract, first of all, key concepts, key entities, so everything that has a name, right? So then you get kind of the terminology that describes your domain of interest. Once you have done, you start to do kind of searching for higher level structures. You search for topics, for communities, so which are kind of extracted using typically some sort of clustering method from the network of information that you have collected. Then you look very carefully at these structures. You identify who are, for example, the influencers on this topic, which has been an event that mentions this entity, and so on. And then you start also to produce correlations, and that's what at the end is called insights, right? So insights is the word you have to use. Okay, now, the reality is, of course, not so linear, right? This is not a process where you start 1, 2, 3, 4, 5, 6, but it looks more like this, and this is just a fragment of what is really going on. So typically you come, you have your question, which is a sort of terminology, then you collect the data, but then you let the machine analyze the data that you have collected, and it may come up with suggestions. It found other terms that you have forgotten, but they are very strongly correlated with your topic of interest. So you go back to step number 1, and you recollect data with the new terminology, and so on. Once you have the data, you find the structures, but then you find that this is a topic of interest and this is not interesting, so the human will decide we throw away all that is not interesting, you redo the analysis, and so this is also kind of a recursive process. And finally, you find interesting stuff, and what typically happens then is that as soon as you find interesting stuff, people will have new questions, and you start again from field number 1. So it's a highly recursive process that involves steps that are executed by humans and by machines. And I just want to give you a few examples of how this looks in reality. And so it's something we're working on now, and it's very interesting. So for example, the problem of creating terminology. So it's very, very difficult for a human to come and say, I will find the vocabulary that will specifically define my field of interest, right? So a human might come and say, food, right? I'm interested in food. Everyone is interested in food, of course. Now, what we did is, we took a huge collection, small collection. It fits on my machine, so it's a small collection, 50 million tweets. And we applied an analysis method that is based on deep learning, which kind of structures the space of terminology in a semantically meaningful way. Not only that today no one can explain exactly what that means, but everyone understands looking at the results that they are good. And you use that to basically expand your terminology and to identify what are potentially interesting dimensions for your analysis. So if you enter food into this semantic representation of the word space, you will get back terms like chemicals, fat, calories. So the human might think, oh, that's interesting. These are food ingredients, right? So let's focus on them. So you have to suddenly determine a dimension of interest. So you give to the machine these terms, and the machine will now start to search for more terms, right? It's kind of a relevance feedback method. And the machine will propose you more terms like fructose, fats, and so on, and the human will continue to choose those that are interesting. The machine will, of course, often also propose things that are probably related, but they are not food ingredients, right? The machine cannot make that difference. It knows just that also, let me give a grain is not necessarily a food ingredient, depends a bit on the interpretation, but it's still clearly related to food, okay? So this is a kind of a recursive process. It's a dialogue between the machine and the human. And once you have decided for a specific dimension, like food ingredient, then you will, at some point, you have exhausted all the terminology that there is, and you get a clean vocabulary that describes all that has been said in this document collection about food ingredients, all the terms that have been used. So this is the first step. That's very useful because if you have such a terminology, then you can get a lot of more data out of your sources that is relevant to your problem. So here's a comparison between data that we have collected on processed food using 7 terms that have been chosen by human experts. And this is the blue curve that you get. And the other one is the one that you get if you are adding all the additional terminology around food. And this gives you about 10 times the volume of data, which still is highly relevant to your problem, which you would have completely missed. And if you completely miss it, you risk, of course, also to somehow miss the important findings. Or another example, what you can do with that. So this is an illustration of what these word embeddings do. So, and I invite you, it's a bit small, the font, but to invite you to look at it a bit and to think about it, right? So these are all the terms on food ingredients that I could identify. That takes like 30 minutes or so. It's not a big task. And then you look at it, and you look at it, and then your human brain starts to analyze it, and you will start to see things, right? Since I have to finish my talk in 2 minutes, I will accelerate the process now. But what you see is clearly that, for example, down left, it's kind of all ingredients that have a positive connotation, like vitamins, right? Then you go on the other side, and then you see, there's all the stuff we don't like so much in the food, right? And then if you go further, you will see up there, it looks like everything is more or less natural stuff, and down there, everything is artificial stuff. So that is not a human who has found this, right? So the machine has found these dimensions. Just a human interprets like that, right? The only thing I did here is the arrows and the labels on the arrows, right? But this is another example of how human intelligence works together. The machine detects the structure, the human interprets it. And this is, of course, now extremely useful because now I can have new categories like everything I like to have in the food and so on, and continue with my analysis. Another thing you can do on this is, for example, analyzing all social interactions. So if you do that in the domain of processed food, you will clearly identify, it's not easy to read, but that, for example, the most important discussion is about genetically modified organisms, which is strongly driven by the US discussion on labeling, right? And so now you find communities that are discussing specific topics. Now we will start, of course, to relate those communities to these dimensions that you have identified before. And in that way, you will start to get insights like, who are the people on the Twitter space that are talking about my company, right? For example, Nestle is one example of such a company. And this gives then some surprising insights about what probably should be done about talking to those people, right? But you can find other stuff. So I come back to our word embedding. So here, I'll put all the countries I could find in this Twitter space, right? And I don't want to read you all the details, but if you start now to look at it, you will start again to interpret things, right? So basically, you may think that the position of the country has something to do with this coordinate system, right? So, and you see things that make sense, at least to me. So Europeans are much more concerned about sugar and salt and all these kind of things, whereas people, I talked to a PhD student from Vietnam this morning and showed him the point, and Vietnam, that's much closer to pesticides and other questions. And he confirmed me, they're very much concerned in Vietnam about these things. And then you see that, for example, the vitamins, they are obviously closer to the countries that are in need of vitamins, and so on. So you start to understand a bit the position of different countries, and of course, I will not show where all the companies that are presented here today are positioned in that coordinate system, right? Though I might imagine some of you might be interested to know. Okay, so and this was an example of how basically applying unsupervised learning on big data sets can give very surprising insights, but it's very closely linked to the interaction with the human who guides the system and interprets the result, right? Because if you tell the machine just at the beginning, find interesting stuff, the machine will, yeah, find something, right? Which might be completely uninteresting to you. So, and then this interplay is really something we're trying to explore, how to optimize it, how to create processes that make it effective, that guide the users really very quickly to the findings they are interested in. I think that's one of the big questions we have today, of how we can take advantage of these big data analytics methods in the best possible way. So just to conclude, I think big data has a huge potential. We all agree on that. And I hope I convinced you that the humans will stay in the loop, at least for a very long time. And we have to think very carefully of how to organize this. Identify 3 types of interactions, so we can think about it. The human can be at the beginning of the analysis, the human can be in the middle of the analysis, or the human can be at the end of the analysis for interpretation. And also, I have seen there's quite diversity of ways of how to implement it. So even knowing the principles will not help you too much. If you want to tackle a specific problem, because there's no one-size-fits-all solution, you have really always to understand the problem. How can you apply those principles in an optimal way to really find the solution that you're after? Thank you for your attention.
Okay, thank you very much. It was very clear, very interesting, very promising, but a lot of questions are still remaining. Is there any question in the room?
Okay, hello. I'd just like to know how many languages you have tried for example, the credible of the website content and something like that. Yes, for example, or for sentiment analysis on different things. How many languages you have tried?
We did in 2 languages, actually.
Okay.
We did it in English, of course. And since we were working with a partner from Poland, we did it also in Polish. I never understood a word there. But it's a very interesting exercise to work with languages that you don't understand at all, because then you understand the difficulties for machines to understand what you try to analyze.
Okay, thank you.
Other questions? Just a question from my side, because I was wondering during your presentation how you can deal with some abbreviation or changes in the Twitter languages, for instance, because a lot of people use specific words and so on, and how can you deal with this kind of stuff?
That's one of the fascinating things, these word embeddings today too, right? Essentially, in a nutshell, what the word embedding does is it searches for analogies, right? It looks, is a word used in a similar context like another word? And then it does a lot of number crunching to get this out of the data. But this has the nice side effects that, you're not constrained to any syntactic conventions or whatever, right? If on Twitter someone decides to call, and this is a real example, Monsanto Monsatan, then the machine will find it because people use it in very similar contexts, and you will find abbreviations. You can follow probably evolution of the terminology in a community and these kind of things.
Okay. Other questions?
Thank you for your talk. How do you manage the map you showed us? Which statistics are behind?
In short, it is, it's based on, as I said, on word embeddings, which project a huge, very high dimensional space, millions of dimensions, right, to typically 200, 300 dimensions. Mm-hmm. So, and this compresses the semantic information, right, which you would otherwise even not see. But then how to go from the 200 dimensions to the 2 dimensions, it's still an interesting problem, and that's an area of active research at the moment, because maybe some of you have seen these things. The phenomenon is very interesting. You see always something, right? You have always immediately associations between things, you group the information and so on, but we don't quite understand how to control in this dimensionality reduction the semantics of things, right? Because the dimensions somehow seem to encode semantics, as we have seen in the small examples, but how they interplay, how you properly project and all these things, that's a more difficult problem. So we have some ideas about this.
Okay.
Yes, a question about your methods as well. To what extent can we still use this kind of approach when the data set is smaller? You talk about a small data set of 50 million tweets. I'm, let's say, considering 1,000, 10,000 values at most, with even larger variability. So to what extent we can apply this kind of methods when the data set is smaller and the variability is bigger?
Yes, okay. I mean, certain methods are not applicable to certain problems, right? If you apply deep learning, you typically need really a lot of methods because you have to train a lot of weights in a network, and with a few samples it will learn not much, right? So from experience, just to give you an example, in the Twitter space, if you're below 1 million tweets, you will get just noise between 1 million and 10 million. You start to see things, and up from 10 million it starts to become more and more reasonable. If you have others, then you have to resort to other ways, right? Like supervised learning, where you can work with relatively low numbers of samples. You can obtain labels through crowdsourcing, which you can do for, if you have only 1,000 or so samples, then you can do that and you go that route. I mean, unsupervised learning will give not too much in that cases.